So I'm going to talk about the economics of agricultural input management with a focus mainly on fertilizer management. And fertilizers, inputs generally, but fertilizers are a very important input for farmers. It's in many systems it's the input they spend the most money on. It can make the biggest difference to their production, as this slide from Africa shows, with and without nitrogen fertilizer. We know, well, what do we already know about fertilizers and their impact on agriculture and their usage within agriculture? So this is a slide with a very long time frame, goes from 1880 up to almost the present. And you can see that over the long term, agriculture's use of fertilizers has increased pretty dramatically. Although in the last sort of decade or two, where there's more data, you can see that it's not rising, and in fact in some countries it's been falling, largely as a result of different policies that have been put in place to try and make that happen. From year to year, the usage of fertilizers varies quite a bit in response to climatic conditions or economic conditions, prices. And the intensive fertilizer use is most concentrated in areas where cropping is most dominant. And so here's a couple of maps from the US, and you can see the places where the red is the really most concentrated use of, in the top map, nitrogen fertilizer, and in the bottom map, phosphorus fertilizer. So this is pretty important to know about when you're trying to manage things like water pollution arising from these fertilizers. So I'm going to talk about a few different questions that relate to inputs in general, but with the examples I'll give will all be for fertilizer and often nitrogen fertilizer. So I'll be, through the course of the presentation, I'll talk about questions like, what is the optimal fertilizer rate for a particular crop in a particular situation? And how do we decide that? What sort of thought process should we go through to make a judgment like that? How do other rates, other than the optimal rate, compare economically to the optimal rate? Do farmers overuse fertilizers? It's sort of many people believe that they do, so let's look at some evidence on that. How should consideration of risk affect fertilizer use? Risk is something that farmers worry about quite a lot, and the use of fertilizer does influence the riskiness of farming, so how do those two things interact? And then how can we think about reducing the impact of nutrients from fertilizer on water bodies? So very squarely in Darryl's area of interest. So we'll sort of range around a bit in between those questions. I'm not going to deal with those quite in that exact order, but we'll sort of jump in and out of those questions a little bit as we go. But let's start with the first one. There's a range of people here with different backgrounds and different interests, including some people with pretty high training in economics and then some with none at all. So I need to try and keep everybody with me. So we'll start with some fairly simple concepts that will be very familiar to some people in the room. So how do we decide on optimal rates of fertilizer? Well, how would a farmer think about optimal rates? Or how do people who are recommending to farmers what the fertilizer rates should be, what do they consider? So non-economists often think about this as a biological or a physical, chemical, biochemical sort of a problem. So it's not very hard to find recommendations like, or pieces of discussion like the one I've just grabbed off the internet there on the screen, that talks about loss of nutrients from a field and replacing those nutrients by applying enough fertilizer to exactly offset the losses. Economists don't think like that. We try to think in a more flexible way about what the options are. So we'll often say, well, sure, tell us how much nutrients have been taken out of the field, but what we're interested in is what will be the performance of different possible rates. And then we'll weigh them up. So on this graph, this is an Australian example, I've got different rates of nitrogen fertilizer along the horizontal axis, and I've got crop yields on the vertical axis, and you can see the relationship. As we apply more fertilizer, the yield on average is expected to increase, but it doesn't increase at the same speed. It slowly flattens off, and eventually it can become completely flat. In some years it can even fall at very high rates. So That's sort of a typical shape that we would expect. So on the left-hand graph, the graph is about yield as a function of fertiliser rate. On the right-hand graph, I've converted that into revenue from the crop, and all I've done is multiply the yield by a price, the sale price of the grain, and you can see it's basically the same shape. Okay, so there's a starting point. We've got some revenue. So then we're saying, well, fertiliser doesn't come free. How are we going to sort of balance up the cost of the fertiliser with the benefits we get from applying different rates of fertiliser? And so on this graph, down the bottom, I've added in a line which is the cost of applying fertiliser at different rates. And so it's going up as we apply more and more. And then we want to subtract the cost from the revenue to try and get a handle on, well, where's the best spot? So in that case, I've subtracted the cost from the revenue, that bottom line. And you can see the shape. We've got it comes to a peak and then falls. And if we take out that other line, which is a distraction, and leave us with that net revenue line or a gross margin or a profit line, you can pretty easily spot where the best spot is for a farmer to apply. In this particular example, it's at about 50 kilograms of nitrogen per hectare for this location with this particular crop. So that's interesting. There's a start point for us, 50 kilograms a hectare. I need to put my glasses on. So the first observation is that the nitrogen rate that maximises profit, or the input rate generally that maximises profit, is somewhat less than the rate that maximises yield. So if someone's setting out to maximise yield, that's all very well, but it will mean that you're sacrificing some profit, because you need to allow for the fact that getting to this maximum possible yield costs you more than the extra benefits that you get. So once you sort of trade off the declining increase in yield and the increase in cost, which is linear, you end up with a maximum profit at some lower rate. Rather than 90 or 100, it's back down at about 50 in this case. The second point to make is that the results of this sort of analysis depend not just on the biology, but on things like the price of the fertiliser. So here's an example where I've got the current nitrogen price, and then the lower curve there is what if we doubled the nitrogen price, and you can see the whole curve has moved down, but it's moved down more on the right hand side because there's more nitrogen being applied there, and so the peak of that curve is further to the left. So that's one situation. Another situation would be the grain price could vary from year to year. So if you increase the grain price, it turns out that it's optimal to apply more of an input. And so the point here is that this decision about how much of an input to apply is not just a biological decision, it also depends on economic considerations like the costs and the prices. Now that sort of approach of teasing out the benefits and the costs of fertiliser rates and trying to come up with an optimal rate has been known about for 50 years or more. It's in very early textbooks in economics, and in some places you can actually get advice of where that sort of information has been pulled together, evidence about the shapes of those curves has been collected locally, and it's available. So this is a grab from a US online system in the Midwest, where you can plug in, a farmer can go and plug in the soil type, the region, the crop type, where they are in the rotation, and they'll get a graph that looks exactly like what I've just shown you with the revenue, the cost, and an indication of the optimal rate. So that can be done, and in many places it's done. Okay, so that gives you a sort of a feel for thinking about economics and input rates. Now I'm going to sort of diverge, and then we'll come back. The next question is one of the ones on the earlier list is, do farmers overuse fertilisers? And so I'm going to just spend a little bit of time on this and just give you some evidence from one particular study, an American study by the USDA. And here's sort of the bottom line from the study, the punchline. It says that nitrogen is applied at more than the benchmark rate on 36% of corn acres, and by quite a lot, on 19% of cotton, on 22% of spring wheat, and on 25% of winter wheat. So it's not that all farmers overuse fertiliser, but a significant proportion of them in the US do. And my judgment would be that in most developed countries, you could probably find pretty similar sorts of proportions of the local farmer population that is sort of hedging their bets, being a bit cautious, applying a bit more fertiliser than they strictly need to, and ending up with more nutrients being leached or more nutrients ending up in runoff and causing pollution problems. One observation I would make about this particular statement is that they refer to fertiliser rates relative to a benchmark rate. That benchmark rate wasn't an economically optimal rate. It was a rate determined on sort of a biological basis. So if you compared it to the economically optimal rate, you'd find even more farmers overusing fertilisers relative to the economically optimal rate. So there is an opportunity there for us to potentially have a win-win, but not for all farmers. It's a matter of, is it feasible to actually identify the particular farmers who are overutilising their fertilisers? All right, so that's really sort of by way of introduction. Now I want to start talking about the paper that Darryl mentioned, which is looking at how, I've talked about optimising fertiliser rates as if that's what we should be doing, but actually it's pretty interesting when you start to look at other rates other than the optimal rate. So let's have a look at that. If I go back to this particular graph, which I've already shown you, which has got it's the relationship between a fertiliser rate, the profit, and you can see the typical shape, a bit of a hill, and ask the question, what range of nitrogen application rates would give payoffs within 5% of the maximum payoff? The maximum payoff's at 50 kilograms. The answer to that question is anything between 22 and 80 kilograms of N. That's pretty amazing, don't you think? Right? People put a lot of effort into making specific recommendations about fertiliser rates, but actually it's an extremely forgiving system. It's extremely forgiving in terms of what rate you actually choose. So this is for a particular situation, but this is not at all unusual. If you go and measure the responses to nitrogen fertiliser around here, you'll find a very similar sort of result. So let me show you some other examples. This is another Australian example looking at the application rate for lime to combat soil acidity. Anything between 2 tonnes a hectare and 4 tonnes a hectare gives you basically the same thing. So in that analysis, which I was part of, we found that the optimal rate was 2.7 tonnes a hectare, but who cares? 2.7? I mean, anything between 2 and 4 will give us basically as good a result as we could possibly want. And in fact, it's not really 2.7. The amount of guesswork that goes into creating a graph like that is so big that you don't really know where the peak of the curve is anyway. Here's an example from Minnesota. This is corn in Minnesota. I think that's possibly the flattest I've ever seen. That's the payoff function, the net benefits of different rates of nitrogen fertiliser to corn. Huge range of rates that give basically the same profitability. There's 2 lines there. I'm going to come back and talk about the second line a bit later on, the blue line. And even this one, which I've already shown you, has the flat. It's not as flat as some. It's a little. The red one is the one I'm talking about. That's the net payoff curve. It's a little bit pointier than some of the ones I've shown you, but it's still got a flat area. So that shaded area in the middle is the range of nitrogen rates that would give the farmer a profitability that's within $1 per acre of the optimal rate. So even $1 has quite a wide range of potential rates associated with it. And if you say $5, it's really wide. And here's some new estimates that I and some colleagues have been making. This is from various sources. So the graph on the left shows an estimate of the nitrogen, the payoff function to nitrogen application across a range of states in the US. The states are listed below it. So that's comparing or combining lots of different locations. And the one on the right, and the blue and the red are different rotation stages. So the red is continuous corn and the blue is corn after soybean. And the one on the right is the same location, but lots of different years. And you can see in both cases, there's a very wide area of nitrogen rates that would give pretty close to as much money as you can possibly earn. So it's really interesting that this is such a compelling issue, such a surprising and seemingly important issue, and yet it's not really very well known. Not many people are sort of aware of this as a fact. And there was a paper published in 1975 in an Australian journal where an agronomist was quoted as saying that when he told other agronomists about this flatness of the payoff function, he observed such reactions as complete disbelief, blank incomprehension, incipient terror, and other reactions that are less readily categorised. So, but I think possibly that's not changed all that much. It's not really an issue that's out there, which is really surprising because you can see from the date on that it's been known for a long time, but for some reason it just hasn't really diffused out and become public knowledge. It's like it's this little dirty secret in the economics of inputs. So, well, why am I saying it's so important? Well, let's look at some of the implications of these flat payoff functions. And the first one is around flexibility. The fact that the payoff function is so flat for such a wide area means that there's a significant margin for error. It means that there's not a lot of point in worrying about getting very precise about what level of an input of this type you're going to apply. Failure to optimise doesn't really matter very much. And so a simple decision heuristic might be good enough. No need for fancy decision tools, fancy computer programs, lots of simulation models. It's a waste of time in most cases. But it does mean that maybe you could bring in other factors other than profit that you care about. Things like the riskiness, I'll talk about risk a bit more later on, personal preferences or personal interest, or financial considerations. Maybe you're short of money in a particular year and it might help, knowing about this might help you realise that actually you could just cut back by 30% and it wouldn't really matter that much. Second implication is around variable rate technologies. There's been a lot of interest in precision agriculture. There's a whole variety of different types of precision agriculture technologies out there. In these comments, I'm only talking about one of those, variable rate technologies. But you can probably see where this is going. If precision doesn't matter, why are you worried about variable rate technologies? Okay, so precision ag variable rate technologies are a response to observing that there's quite a lot of spatial variation in most crop fields. So there's a map there that sort of shows you what somebody's estimated low, medium, high levels of yield in a particular field, and that's really common. And so one thing you could do in response to that is try to adjust the input rates to make best advantage of the low, cut them back in the low areas and boost them in the high areas. And that, if you did it, would certainly, and if you were accurate about where the high and the low areas are, that would certainly give you a higher revenue and a higher net revenue probably than trying to apply a uniform rate. But usually not by very much, only by quite a small amount. So let's show you how that works. Suppose, just to keep it simple for the purposes of explanation, suppose we've got a field and that the field is there's three areas of the field with high, medium and low yield potential. And these yield response functions on this graph are for those three areas. And you can see each of them has reasonably wide flat payoff sort of area within them, but the peak level of the peak fertilizer rate is different for each of them. So on the highest yield potential curve, the optimal rate is up at around, looks like about 300 in this particular example. On the low yield potential, it's down at about 140 or something like that. And on the middle one, it's at about 200. So they're quite big changes in fertilizer rate that are recommended between the different parts of this field. There you go, that's actually listed there. The optimal land rates is 133, 203 or 274 kilograms per hectare. So big differences. But if you were to do that perfectly and vary your rates according to which yield potential was present in that field, the improvement in profit is only 1.7%. A really small increase for big changes in the rates. And so why is that? So let's talk that through. Now we've got people looking at different screens, so I can't use the pointer very effectively, and people also online. So I'll try and talk it through. Let's look at the top curve there, which has a peak at 274 kilograms per hectare. There's a dotted line that runs through the top of that curve, right? So that shows you the profitability of applying that high rate of fertilizer. And Then just below that, there's another dotted line which says, well, what's the profitability in those parts of the field if I don't adjust the fertiliser rate? I stick with 203, which is sort of the best average rate for the whole field. You can see how close together they are. Like you adjust the rate for the high yielding area and your profit does go up, but only by a really small amount. And similarly for the low yielding area, you can get a little bit more by cutting your rate from 200 to 130, but the increase is really small. And when you weigh up across the field, the overall increase is only a bit over 1%. So here's another example from, this is out of the paper that Darryl referred to. This is looking at the incremental benefits of increasing the precision, I've called it the information intensity, of decisions about lime application to treat soil acidity. So this is saying, suppose we just have one uniform recommendation for the whole state. Then let's compare that with a situation where we break the recommendation down by soil type, by region. And so by the whole state, I call that very low precision. By soil type, by region, I call low precision. And then moderate precision is we're going to make a separate recommendation for each field. In this study, we didn't go to high precision, like varying it within a field, but even going from very low precision to low precision, so we got some benefits. Going from low to moderate, you can see we've got a lot less benefits. And going from moderate to very high, you get even less. So then the last one's not shown on the graph, I'm extrapolating, but I'm sure that that's true. So there's as well as a diminishing benefit from applying more fertiliser, which I showed with the fertiliser graph, in this case, there's a diminishing benefit from applying more information. Right? The more you bring big data into this realm, sure you get more, but the gain falls steadily as you apply greater and greater detail into the analysis. So here's a quote which I really like, which is actually, again, the date, 1975. So this is a quote from decades before precision variable rate technology was even dreamed of. So Jock Anderson, an Australian agricultural economist, said, in pursuing optimal rates of decision variables, precision is pretence and great accuracy is absurdity. So he was well ahead of his time, although it's an insight that hasn't been sufficiently recognised. All right, how am I going for time? Half past. Let's talk about a completely different issue, but another implication of the flat payoff functions that we've been looking at is around the benefits of research. So depending on the type of research we're talking about, it could be that the research isn't worth as much to farmers as you hoped it might be, particularly research that will help people make decisions about input rates. So here is an example. So it's labelled figure 8. And so the first, let's suppose that without conducting the research, you have a perception of the yield potential in a field which is relatively modest. So that low curve is labelled the perceived payoff without research. And the bottom axis is the input level. Then you do some research and you find that actually you were wrong, your perceptions were wrong. This is a much more high yield potential situation than you recognised. And so now you're on the top, you realised you're no longer on the bottom line, you're on the top line. And so you can see that the peak of the curve is higher. We've gone from input level 1 to input level 2, becoming the optimum now. But again, the gain in profitability is pretty small. It's the difference between those two lines, those dashed lines that are close together on the top curve. If we'd stuck with I1, we would have got that profit level P12. But if we increase it to I2, we get a profit level P22. They're hardly any different. So in terms of how much gain did the farmers get from the research that told you were at this higher input potential higher yield potential than you thought, really not very much. Interestingly though, research that could actually not just change your perceptions, but actually change the yield from the lower curve to the higher curve would be worth a lot. It looks like you've basically doubled your profitability from this field, and that's right. You could rather than this little tiny sliver of benefit. So that's, as a rule of thumb, it may be more difficult, but if it's possible to actually generate a new technology that changes the yield, as a generalization, it's much more valuable than a piece of research that gives you information about the yield. Right, so that's another implication of flat power functions. And the last sort of these implications I want to talk about is externalities. So a piece of economic jargon meaning impacts on other people who aren't involved in the decisions that you're making. So an externality is water pollution or greenhouse gas emissions, where other people are suffering the consequences of an economic activity that you're doing. So externalities are quite important when it comes to fertilizers. A lot of water bodies, including in Canada, the Great Lakes, are greatly affected by water pollutants, and it's a big issue around the world, and a big issue largely coming from agriculture. Okay, so what's the implications of flat power functions here? Well, for one quick comment you could make is that if farmers are over-fertilising, one perspective on this is it's probably not costing them very much. So if they have their own personal reasons for over-fertilising, they feel comfortable with over-fertilising, there's not a lot of point in you telling them you could make more money by cutting your fertilisers. Because actually, although what you're telling them is true, the amount of extra money that they can make is probably so small that it's not going to motivate them to change. So there's little financial incentive to cut back. That's the sort of the bad news. Maybe you can turn the argument around and say something like, but there's no financial benefit from over-fertilising either. So this is I've showed you this one before, to come back to it. This is a study that was done, as I said, for Minnesota. And the study's called Determining Socially Optimal Rates of Nitrogen Fertiliser Application. It's done for corn. And the red line is a sort of an average response function. And as I said, it's particularly flat, but the peak level of benefit from nitrogen fertiliser is at a rate of 165 kilograms per hectare. And then the blue line, what they've done to calculate that is try to estimate the off-site impact from the nitrogen application. So they've made an estimate of how much of the nutrients make their way into groundwater or surface water, leave the field, end up in a water body, and contribute to an algal bloom or whatever problem that they cause. And they've quantified that, they've converted it to dollars somehow, and they've plotted on there the blue line, which is the net social benefits of applying nitrogen fertiliser in Minnesota. So the first thing you can see is that the off-site impacts are quite a lot smaller than the benefits of using fertiliser. So it'd be hard to win an argument saying we should stop using fertiliser because the benefits are substantially larger than the cost. The off-site cost, especially at least in this case. That won't necessarily be true in every single case, but this is an example where it clearly is true. But the second really interesting observation is there's the flatness of both of those curves. And so although they are saying that it would be socially optimal to reduce rates from 165, which is where they think the farmers should be, to 137 kilograms per hectare, if you look at the red line, the dashed line hasn't even left the ink of the red line, right? It's so flat that you'd be hard pressed to even measure any difference in profitability between them. So the cost to farmers, or the reduction in profit to farmers from going from 165 to 137 is almost vanishingly small in that case. So that's good news, right? So maybe that generates some opportunities for us. We'll come back to those later. Okay, so I want to go to a yes but issue now. So I gave a presentation a bit like this to a room full of 300 farmers in Australia last year, and generated a really interesting discussion at the end, but there was a couple of yes but questions. And the main one was, yes but what if I'm fertilising in order to get the quality of my wheat high enough in terms of the protein content of the wheat that I qualify for a higher price for my grain? So in Canada as well as in Australia, at some level of grain protein, your price jumps, and it's a step function. And so so that says something. It's a step function. It doesn't go up smoothly, right? So that means that something could be going on there that might affect the conclusion that I've been talking about. Okay, so I don't know what the premiums are here, but in Western Australia, if I can get my protein above, I think it's 13%, the price of my wheat jumps by $9 a tonne. And so if I put that into my graph, and if I say that level of protein will be achieved if I can apply at least 60 kilograms per hectare of nitrogen, then you can see what happens. On the line in the graph, when I get to 60, there's a sudden step up. I've lost my flatness. Okay, so all those, if that's the right graph, all my arguments that I've just been giving just sort of disappear. Okay, so fair enough. The payoff function is no longer flat. But we don't really know in advance, usually, what level of nitrogen fertiliser will get you to that threshold level that will qualify you for the increase in price. So although the price step itself is a step, it's a vertical step up, there's all this blurring around the probabilities of what level of fertiliser will actually get you to that step. And it would be affected by weather, it could be affected by soil conditions, so you don't really know. So this is just an illustrative example. Let's suppose that a farmer is looking at this and saying, okay, what fertiliser rate will give me the step up and give me the higher price? My subjective assessment, I'm the farmer, is that there's a 33% probability of getting the price premium if I apply at least 60 kilograms. There's a 2/3 probability of getting the price premium if I apply at least 70 kilograms. But I'm absolutely certain that I'll get it if I apply at least 80 kilograms. What does that look like? Now, the flatness is back. In fact, it's even flatter, right? What I've done now, the flat area goes for a wider range than it did before. Okay, and in fact, it's even flatter than shown on that graph, because that graph has got little steps in it, because I've artificially said it has it at 60, 70 and 80. In actual fact, it's 60, 61, 62, 63, 64. There's a little step at each of them where there's a probability of getting that price premium at each of those rates. And so as long as if you're thinking about boosting your nitrogen to chase a higher payment, the flat story applies with full force. Okay, talking about risk. This is not so much a story about flatness, but it's a story that relates to the issue of thinking about environmental benefits from reducing nitrogen and phosphorus impacts on water bodies. So risk is part of that. Now, if you read the literature about nitrogen fertiliser rates, it's not very difficult to find somebody who will write that farmers apply too much fertiliser because they try to avoid risk. They have an attitude that a way of reducing my risk is to boost my nitrogen rate, and then I can be more confident of getting a high yield. That's the sort of the mind game that people say. So some people suggest that increasing nitrogen is a way of reducing your risk. Interestingly, the actual empirical evidence shows the exact opposite of that. So I'm going to show you a couple of bits of evidence. This is a modelling study. I'll show you some statistical results next. So this is an Australian result showing the effect of increasing nitrogen rate on wheat yield. And it's a box and whisker diagram. So the green and the blue boxes are 25% and 25% down, 25% up and down, either side of the median. And the whisker, the line with the T at the top and the bottom, that's a 95% confidence interval. And you can see that as the nitrogen rate increases, well, what would you say about that? You would say that the variation in yield increases. So in that sense, the riskiness of production increases as you go from low rates to high rates. But within the range of the optimum, which in this case is probably about 60 or 70, it doesn't increase by much. It's actually another flat thing, really. The riskiness is a measure of riskiness will be pretty flat, close to the optimal fertiliser rate. So there's one example. Here's another one. I showed you these graphs already, focusing on sort of looking at the mean, but let's now look at the riskiness. Same sort of graphs, box and whisker. So these are for a range of US states. If you look at the left-hand one, where we've estimated average graphs across a range of states, you can see that risk does go up perhaps, but by very little. Pretty much doesn't change much. And the one on the right is different years at the same location being lumped together to give you an estimate of riskiness at that location. In that case, there is a significant increase in risk as you go up to a certain level, and then it sort of flattens off. Okay, so you can see what I'm doing when I do this. I'm looking at the spread, right? The vertical spread either side of the median as my measure of how risky production is at that particular nitrogen rate. So it's the opposite of what people think. It's not more risky to apply. It's not less risky to apply more nitrogen, it's more risky. And one more element of this is that's only from the perspective of yields. Okay, so that's saying that as you apply more nitrogen, your yield variation increases, and so your risk increases. In addition, on top of that, there's a price risk as well. And so I haven't shown you how I've done it, but I've summarised the impact of price risk on the riskiness of grain production here, and the width of those two dotted lines is an indication of the riskiness. And due to price, it actually also increases. So the two of them combine, yield and price both combine to mean that more nitrogen is more risky. So that's a pretty interesting thing, that a common perspective on risk is sort of wrong. It's sort of backwards. Okay, so this is my summary of what does it mean for nitrogen rate. If risk is unpredictability of profit, which I'm asserting that that's the best way to measure it, then increasing nitrogen rate does not reduce risk. Near the profit maximising rate, an increase in nitrogen leads to a slight increase in risk. And avoiding risk means reducing the nitrogen rate, but not by much. And when you do this, you're almost certainly still on the flat part of the payoff curve anyway. But when would it make sense to increase your nitrogen rate? And the answer is if you can predict higher yields or you anticipate higher prices, then it makes much more sense. But to do it as an insurance policy, as many people talk about, actually makes no sense. It's not an insurance policy at all. It's actually an anti-insurance policy. Okay, let's go to, I've already talked about the effect of fertilisers on water pollution. Let's have a conversation about how can we do something about water pollution. So through that conversation, there's various things I want to pick up that will give us some levers or some clues, some ideas to think about responses that we could do, policy approaches that might be useful. The first thing I wanted to highlight is that last year I took a sabbatical at the University of Minnesota, and I worked on a particular project where we were looking at water pollution from agricultural fertilisers. And one of the things we did was to review the existing literature on the possible ways of reducing loss of fertiliser nutrients into water bodies. And there are lots of options, right? So there's a big literature about possible ways. They've been reviewed, the economics have been done. And so all these options are there. Some of them are sort of agronomic, some of them are sort of outside the field, like buffer strips or constructed wetlands. But some of them are inside the field, like nitrification inhibitors, which stop sort of the chemical processes that allow nitrogen to be lost from the field. Zero-till, and the bottom one there is reduced nitrogen rates. My conclusion from this review is that the one thing that I had the most hope for out of all of those was reducing nitrogen rates. All of the others were either commonly quite expensive or not very effective. It seems to me that reducing nitrogen rates is the only one on that list that has the potential to be both cheap and effective. All right, so we've already talked about this a bit. So this is where the flat payoff functions come back in. It seems like there's an opportunity here, because if a farmer reduces the fertiliser rate below the economic optimal level, profit falls, but only a little bit. And the percentage reduction in profit is much less than the percentage reduction in fertiliser. So does this give us some opportunities? So one of the things we did in this work I was doing in Minnesota was estimate a whole lot of these curves to try and say how much could we cut rates by, how much could we cut rates by and not lose more than 5% of the profit from these crops? And without going into all the details, you can see on those curves, there's a bunch of black lines. There's a black dot, and to the left of the black dot, there's a little line that shoots off to the left. And that's showing you how far you can go down from the economically optimal level and still be within 5%. Right? So you can get a sort of a visual perspective on that. But if you look down at the little table on the right, there's a summary of those results. And it says that for continuous corn, for the study where we looked at a single site and multiple years, you could cut rates by 30% and not lose more than 5% of the profit. Or in the multiple site case, 33% reduction. If it's corn after soybeans, it's even bigger, 45% or 40% reductions in fertiliser rate without losing more than 5% of profit. 5% could still be a significant amount of money, but so maybe you only want to cut it by 2%, right, or 1%. But whatever, there's a trade-off to be thought about there. But there's clearly an opportunity here somewhere along that line. This is a summary of those results showing the average curve, showing that as you cut back from the peak, at some point you cross over the dashed line, which is the 5% lost line. And again, as it was shown in the previous slide, it's a 30 to 40 to 45% reduction as possible without huge losses of profit. So just based on that, what are our opportunities for policy? So there's three things that I've talked about. One is the evidence that some farmers, a proportion, 20, 25, 30% of farmers over-apply fertiliser, even from the perspective of what's in their own interest. Right? So for them, if we knew who they were and we could persuade them, then reducing their fertiliser rates would actually be a win-win. They'd be better off, the environment would be better off. Now, that's not to say that that's easy, because how do you know who they are, right? But there could be an opportunity there. The second opportunity is around the misconceptions about the effect of risk related to fertiliser. So if we could find out who's thinking that nitrogen rates reduce risk, maybe we could do something with them. And the third one is the flat power function story, which is not saying that it's costless to reduce rates below the optimal rates, but it is saying it's cheap. So I think there's opportunities there to think about different policy approaches that we could take to each of those three. And I don't pretend that I've thought them through, but whether or not we're using a persuasion approach or incentive payments, or we were thinking about the possibility of offering an insurance scheme where you could say to farmers, you cut your rates up to this amount and we'll cover your losses, whatever they are. However much less than money than you would have made, we're so confident that it won't be much that we'll compensate you for it, to give farmers confidence that they're not going to face high risks from cutting their rates, as another interesting idea. Okay, I've talked for long enough. Let's wrap this up. So just to summarise what I've talked about, flat payoff functions are really common and they're really important. I've talked about a bunch of implications about the flexibility that they bring, the implications for research, the implications for precision ag. I've talked about the issue of risk and fertiliser rates, and we've just touched on briefly some opportunities for policy to reduce nutrient pollution. And the last one is I offer a free online course called Agriculture, Economics and Nature on Coursera. So if you're interested, you can get to that through my website. It's a 6-week course, 2 hours a week, just to introduce you to the basic ideas in agricultural economics and how they apply to environmental issues.